So our next speaker is Sandrine Lévêque-Fort. She is from the University of Paris Saclay in France. Sandrine has been working quite a lot in the development of also some super resolution techniques related with the supercritical angle fluorescence, and combining these with structure excitation and single molecule localization. Today, she is going to talk to us. The title of her presentation is Engineering Fluorescent Emission for Enhanced 3D Single Molecule Localization Microscopy. So with no further introduction, I'll let Sandrine go for it.
Present from where?
You can go here or here. It's up to you.
Okay, up to me.
Yeah, yeah, you have the controller there.
There's someone to control the slide? Or
yes.
Where? This? Okay.
So green go forward and red back.
Perfect. Hi, everyone. So really happy to be back to a real conference, and thanks to Guillaume for inviting me to come to ELMI, which I really enjoy. So yeah, today I will mainly show you some strategy based on the localization strategy. So as Stefan shown you, so you all know that now that you need this on-off strategy to allow you to localize the molecules. And this allows you then to get this enhanced 2D images. And then, of course, when you're doing this localization process, what you get is only the information in the transverse direction, so the XY. So you need to apply supplementary techniques to get this 3D imaging. Something else I want you to keep in mind here is that when you're doing this Gaussian fitting, for example, you only take advantage of the spatial information. So keep that in mind, and I will see in the second part of my talk why it's important. So when you want to use this 3D strategy, you have the choice in between several techniques and based on, for example, PSF engineering, interferometric, and this will really depend on your applications, if you want to go in depth or have an isotopic precision or a uniform one. What I will show you today is these two techniques based on supercritical angle. That is the only technique that provides an absolute elevation for your the Z information, and also the modulated excitation, which gives you a uniform and in-depth strategy. So if you look at your what you collect usually with your microscope, so if you have your biological target here that emit fluorescence and the probe is located more than, let's say, 500 nanometers from the cover slip, when you collect the fluorescence through the objectives, and if you look here in your pupil, in your back focal plane of your objectives, you only see fluorescence within the critical ring, so that's what we call it undercritical. And in fact, it corresponds to what we call in physics the far field of your fluorescent molecule. However, all molecules, because they are dipoles, they also endow with a near field. And here in microscopy, we are in a very specific regime where, in fact, when the molecule is close to the interface here, the near field that is usually evanescent can become propagative here and reach your camera. So it means that you have this extra information that you can detect, and it's very interesting, because first of all, if the molecule is directly located at the interface, it presents half of the photons that your molecule can emit. So it's quite a lot of information that comes from this supercritical emission. And you can see here that it's really appear, if you're looking now in your back focal plane, it really appears at this supplementary ring of emission. And the very nice things then, because it's an evanescent signal, when the molecule is going further away from the interface, what you will see here is that the amount of supercritical emission that will then be emitted will change. And with this supercritical emission, you have directly let's say, a nano ruler. You can know how far you are from the interface with an absolute manner. So how do you disentangle this supercritical emission from the undercritical one to get this absolute actual information? Basically, you just need to find a way to disentangle within the back focal plane the undercritical that is in inner part from the supercritical here. And here today I will only cover the combination with storm, but it's worth noticing that you can apply this supercritical emission with any microscopy techniques. We combine it with live cells imaging for dual depth imaging, confocal state, so it works with any microscope because you only need to modify your detection site, basically. So in combination with a single molecule microscope, basically you only need to modify what happened before your camera. So here you have the basic single molecule microscope with multiple continuous lasers. And here what you do is you split your imaging path in two arms. So you will have one arm when you collect all the fluorescence on the first half of the camera, and one arm when you block the supercritical. So here, how you will get the information, you will just localize the two events in the two halves of the camera, count the photons in each part, and then just by comparing the number of photons in these two channels, you get the absolute elevation. And what is nice is you don't need a calibration at all to do that, because you can really rely on the initial theory. So you can get then this kind of images on tubulin. So this is the 2D image you will get here. And then when you apply this supercritical detection, you get here, as usual in fausse color, the 3D image based on these techniques that we call Donald. And I didn't forget to mention it was also developed at the same time in the labs of Jonas Reyes. So what is nice, as I've said, is that you get an absolute elevation. So all these values are how far your fluorescence molecule is from the interface. And then if you look at what is the precision, when you are going in depth, you see that you have a very flat precision in the first 300 nanometer, and then because it's coming from an evanescent wave, it gets a bit worse when you are getting further from the interface. So we applied this kind of strategy, so you can see also that you can then zoom in here and see the arrangement in 3D of the molecule. So then we applied this kind of strategy to localize, for example, various adhesion structures. So here, in collaboration with the group of Grégory Janon and Olivier Rossier in Bordeaux, we look at focal adhesion and how they mature and for various states. And in particular, we looked on the paxillin and the quinolin. And then you see that you can probe very tiny difference of Z information from this adhesion structure, because we do have the possibility to do that with the Donald systems. Another kind of structure that we looked at also with, in collaboration with Renaud Poinclou in Toulouse, it was podosome within macrophage. And you see that they can be arranged like you have the shape of these podosomes here with an actin core here and with various proteins that makes the podosome smooth. And then what you can see here is that if you label, for example, here the vinculin, you clearly see the kind of ring structures. And what is nice here is, for example, you can see here it's a radial cut of a podosomes here. And you see here in the 3D for all the molecules that have been detected. And you can see here that we label various proteins, the paxillin, the vinculin, and the actin. And you see also that we label the two extremities of the taline, the N and C terminals. And already from the analysis of one podosome, we could see that there was a kind of stretch between this protein, and that after doing a lot of measurements, and we were allowed to recombine all these measurements because we have an absolute evaluation for all of them, that helped us to redesign another mechanism for the tension on the taline here. So, of course, you might not all want to do just adhesion structure studies. So if you want to go a bit deeper, supercritical angle is also, can be very also nicely coupled to any other techniques like PSF engineering, because you will use the SAF information as an absolute manner and combine and have a common range with a PSF engineering, like for example here, we combine it with astigmatism. So then you benefit of the axial drift strategy because you have the absolute information, and then you enhance also the capture range of your system. So here that's what we did, and here you have a two-color experiment that you can combine, and so you have the actin and tubulin both in 3D here. And if you compare with what you would have get with a diffraction limited, you clearly see the difference. So now we'll move to the second part of my talk this morning, which will show you how you can also have another way to localize the molecules in a wide field configuration. So this idea was triggered by a very old experiment by a French group in 2005, where in fact what they've done is that they have created interference with two, by separating their laser in two here. And they probe some beads attached here to probe myosin 5 steps. And they probe these beads, and they detect the scattering of these signals on the photodiode here, and they did a locking detection. And with this kind of strategy, they get already at this time precision that was a sub-nanometric precision. So the idea was, can we kind of adapt this and change the way it works, because at this time it was really using scattering, so an unlimited number of photons, which is not the case anymore here because now we have fluorescence emissions. We also have to deal with multiple emitters within the field of view because we want to take advantage of this large field of view to have a high content screening. And we want to do a structural measurement, not just tracking. So it means that we have to find a way to convert our system into a locking detection but compatible with a camera. So what we did here is we applied for this pattern, where our idea is to put this new technique into working systems, and we call it ModLock. And this field has been very active for a few years now, and with various acronyms, as usual in a single molecule. So let's look at how the system works. So what you need first is just to replace your wide field excitation for a structure one. So you can borrow any means, like if you know how to do SIMS, you can create interference, and then you will excite your sample with a structure excitation. Now, if you move your structure excitation, your sample, what you would get is a modulated emission from your fluorescence because you have a modulated excitations. So now it means that you will be able to find the position of your molecule here just by using the phase of this modulated signal. So if I stop now the movement of my fringe on the samples and I look on various beads here, you see that this one here, the red one here, is really under bright fringes at the beginning, so you have is a maximal and then will decay in terms of signal. In contrary, this one here is really near black fringes, is minimum, and then will increase. So you see that the difference of phase here of the modulated fluorescence will directly tell you where you are within the fringes. So that you just need to extract this phase within this wide field acquisition to extract the localization information. So you don't need to sweep your fringes all the time. You just need 4 different positions here to sample the modulated emission and then to extract the phase information. So what do you expect in terms of precision? So you all use now to have to hear about this Kramerau lower band, and this is the usual one you would get with a classical Gaussian with no structure excitation, when it's mainly dominated with the square root of the number of photons and your point spread function. And here, what you see for ModLock here is that you still have the number of photons, of course, but what you see appearing here is lambda, which is the spatial pattern period of your structure excitation. So it means the smaller the pattern is, like what you see here, the better the enhancement you will get compared to Gaussian, which is typically be at least 2.5. And of course, when you are applying also structure excitation, some fringes on your sample, you also need a very good contrast. And this is what you see here. The better the contrast, the better will be the enhancement compared to classical Gaussian fitting. So if you look on what is a typical sample, you see here that now what you need is to create this interference. So then you need now to split your lasers in 2 arms here. And then you will focus in the bifocal planes these 2 beams. And you just need to introduce an electro-optic modulator that will do the phase step and move the fringe pattern on your sample. And you can see here that moving this knife edge mirror in and out, you can really play with the position of your beam within the bifocal plane and change the size of the structure excitation on your sample. So you see it's not a big deal to arrange. This is the arrangement we developed and built to go to a summer school in South of France, to go to Mifobio in last November, and this fits in 30 by 30 centimeters, and it supported 8-hour travels by car, so you see it's pretty reliable. So then, what about the detection? You want to extract this phase information. with 4 different samples of intensity. So the easy idea would be, let's take 4 sequential images here, and that should make the tricks. But what you have to have in mind is you are looking at single molecule events, which on definition can start whenever and stop whenever during your sequential acquisition. So it means that, for example, here, this one here would start in the middle here. This one will start at the beginning but stop. Only, for example, this molecule will be visible in the 4 sequential imaging. So if you want to apply this strategy of sequential imaging, it means that if you are looking at and using this Alexa 647, which is so far the best dye for this storm, you see that the mean on time here that we observe experimentally is around 15 milliseconds. So it means that then you would need to have a super fast camera, which you can do with the SMOs by really using a very small subarray. And even in doing so, you see that the number of molecules that you will discard will be at least 30%. So if you want to increase the localization of your system, but you discard a lot of molecules, that's not the way we choose to go. So what we design is another strategy where, in fact, here, at the detection, we will insert a system, in fact, that will sample the fluorescence much faster than what the camera do, and we, in fact, create some replica of the image directly within the camera. So what we do, for example, here, we inserted a mirror here, and this mirror creates 4 different replicas in synchronization with the 4 different positions of the fringe pattern. So you can see here, for example, on a very simple sample of beads, you see that now, if you zoom here, you have 4 different images that correspond to the 4 different positions of the fringe pattern. And you clearly see here that the intensity are different for all of the different beads because they are placed at different positions within the fringe pattern. So you can clearly already see that the phase of all these different beads will be different. So now if we look at the performances of these setups, so if we compare the Kramer-Rao lower band in red here and the data we get from this experiment in blue, you see that we are very close to Kramer-Rao lower band and typically will be with precision between 2 and 4 nanometers, let's say, in the direction where you apply this modulation. You can also directly compare. For example, you can apply the modulation only in one direction. Here, for example, here in this direction and not in the other. So then you see the enhancement directly. So of course, we are mainly, so you can apply in any direction. So we are mainly interested in the lab to apply it in the Z direction. So it means in this condition, what we did is we then apply in the tilted manner. So then now, we keep a single objective configuration, but what we have here, we need to combine the phase information within the structure excitation and the X information to extract the Z information. So some images before, sorry, I will show you the new setups now. So now we also take the advantage to design a new detection here based this time the element that do this addressing in a sub-different part of the camera. Here we decided to create 4 different quadrants here, and here we use the Pockels cells, which is very nice because it can be very stable. So some information about the localization precision. What we have is a precision that is really like below 7 nanometers, which is uniform within the depth of field, in contrary to astigmatism. So some few results quickly. So here on macrotubules, you can see the color-coded is obtained with the modlock here, and you can see that if you zoom here, you can see the X, Y position, and you can see how the macrotubule ruffles. And then you can also zoom here and see that you see the holocore of the macrotubules. So of course, we apply this to go in depth. So for example, we observe clatrine-coated pit at 4 microns. And if you look at the region of interest here, you see that they are forming a shell on the top of the nucleus. And you do have the resolution to see that they are forming some sphere without any troubles. So we do the same things on mitochondria, and you can zoom here, for example, on this one, and you can see that if you do some radial analysis on the mitochondria, that you can clearly see the top and bottom membrane with the same kind of precision, and you can do an analysis here of all the points, so all the dot points here at single molecule events that have been measured, and you can see that you have the same thickness of the membrane, that is the convolution of the primary, secondary, and the precision of the systems. So you can assess that within the whole field of view. So this is what is nice about these techniques. You already have from scratch a very large field of view from up to 50 by 15 microns. And you can have also some images in depth. So here what we've done, and you will be able to see during Abigail posters tonight, that we were able to do also some imaging inside scattering systems. So here it's a collagen matrix. So you have the initial images you would get with a classical system. So you see this is really blurry, but as you just need to have a variation, a modulation of this point spread function, you can still get these 3D images at 40 micron in depth. So now just to conclude, so the take-home message is that you can really take advantage of intrinsic information, just like the supercritical angle fluorescence. So we are working at the moment on various ways to have new filtering, combining with multiple color or multiple red dyes, and also benefit of the wide field excitation that we developed, the Aster technique that offer you a very large field of view. And for the modlock strategy, what we are working on, so on top of this precision that is uniform and really like a very nice, I said, that to image with a uniform precision, what we are doing is also extending the field of view. So you can see now we can get with a super large field of view and image multiple proteins. So just I want to thank the people that did the works for the SAF. Initially it was the PhD of Nicolas and then Clément. For the modlock was a PhD of Pierre and now Abigail. So it's collaboration with Institut Langevin and various groups here. And don't forget to go and see the posters of Abigail on modlock tonight for more information, and also from Caroline, from Christophe Leterrier. And I also want to thank Sabelite for the hardware and consumer lending. And if you are interested, you can go and see them on booth 33B. And now I would be happy to take questions. I think there's no time remaining, sorry.
Yes.
Thanks, everyone.
So let's thank Sandrine. Yeah, again, we're very short in time. We could take one quick question if there's anything. If not, as Sandrine mentioned, you could visit the posters and the booth and talk to her directly. So if there's nothing urgent, let's proceed. Thank you very much. And